Now, examining periodic trends. Properties beyond the electron structure of the atom, which repeat as we look at the periodic table. So, periodic table, of course, gets its name from the idea that there are recurring properties at regular points within the table. So, what are the driving factors behind these properties? Now, certainly the table itself is based largely on reactivity of families of elements. And this has to do with electron structure, and we've already talked about electron configuration at this point. So, what properties of the table lead us to specific properties of the atoms within the table? Why do we see metals to the lower left, nonmetals to the upper right? Why do some families contain both, even though their valence electron configurations are the same? Well, there are three main factors here. First is nuclear charge. Now, of course, as we go through the table, nuclear charge is increasing throughout the table. But this factor really plays its biggest role within a period. So as you go from left to right, within a row on the table, nuclear charge increases, and this is an important factor in determining properties. Shielding effect. Shielding effect is why nuclear charge doesn't play as big a role as you go from the top of a family to the bottom within a column in a periodic table. Now, so what's shielding effect? Well, those outermost electrons in an atom have a large number of core inner shell atoms between them and the nucleus. And so they're protected from the nuclear charge by these layers of electrons. And so shielding effect means that the pull on valence electrons is lower the more shells, the more periods there are for the atom. Now, last effect is electron-electron repulsion. This tends to be a relatively small effect, but we see it particularly when we have filled and half-filled orbitals. Energetically, those orbitals are more stable because of the symmetry and arrangement of electrons. That symmetry minimizes the push of electrons on each other, reduces the energy, increases the stability of those arrangements. So where do we see these in action? Well, one of the first places is the size of the atom. And we'll note that we'll note a general pattern here. As I go from lithium to neon, sodium to argon, potassium to krypton across the periods, and please note we're only looking at S&P block elements here. But as we go across the period, an atom's getting smaller. Well, why is that? Well, they have the same outermost shell, but an increasing nuclear charge. That increasing nuclear charge means an increased pull, nuclear charge being a positive charge because of the protons, the electrons negatively charged. The larger the nucleus, the more pull in on those electrons. And so consequently, the smaller the atom. As you go down a family, for instance, lithium to sodium to potassium, now we see, despite the increasing nuclear size, those additional shells of electrons weaken the pull of the nucleus, and we get an increasing size. We can see that across additional periods as well. Now, what if we want to make an ion? What if we want to pull an electron away from an atom? So ionization energy talks about making a +1 ion, or first ionization energy specifically. These are values charted here for first ionization energies, and we see a perhaps not unexpected pattern. The more nuclear charge within a period, the harder it is to pull off an electron. The more shielding there is, the easier it is to pull off an electron. So hence krypton is easier to remove an electron from than argon, is easier than neon, which is easier than helium. But you'll note jaggedness in the lines here. So beryllium to boron, nitrogen to oxygen, magnesium to aluminum, phosphorus to sulfur, for instance. What's going on here? Beryllium has a full S subshell. Nitrogen has a half-filled P subshell. These stable configurations reduce energy, make it more difficult to pull off that electron. So those stable arrangements, from reducing electron-electron repulsion, are going to require a little bit of additional energy to pull off an electron. Now, what happens if instead of removing one, we remove a second electron? So the second ionization energy, that's the orange line here, is the energy required to go from a +1 to +2 ion. Please keep in mind that's removing one electron. It is not a cumulative energy. Now the pattern looks much the same. The bigger the nuclear charge, and this is of course just within a single period, the larger, in general, the ionization energy. You'll note a big spike with sodium. Well, why is that? The big spike with sodium going to a +1 ion, has lost its sole valence electron, and now its new outermost electrons are one shell down, and so closer to the nucleus, being held more tightly, and it also has a full p orbital now. And so sodium will be more difficult to remove a second electron from, in fact, much more difficult. And please also note, aluminum, having lost a single electron, has 2s electrons now, and so the little bump up. Sulfur, having lost an electron, now has a half-filled p orbital, so the little bump up there. Why, in general, are second ionization energies higher than first, even though we're not talking about a cumulative energy, we're only removing a single electron? Well, remember, we're now removing this electron from a positively charged ion. And so, of course, the negative electron is attracted to that positive ion. Now, one of the most important trends when we talk about bonding is what's called electronegativity. Now, this graph shows Pauling electronegativity values. There are a number of different ways to calculate the electronegativity value, and this is a calculated, not a measured value, as the preceding two charts showed. What is electronegativity? Electronegativity, simply put, is how strongly an atom is going to pull on an electron in the bonding process. The stronger the pull, the higher the electronegativity. And so what's going to make that happen? Well, a large nuclear charge is going to attract electrons well. A small amount of shielding between the nucleus and the outermost electrons is going to increase the electronegativity, the pull on those electrons. So fluorine, all the way to the right, so the greatest nuclear charge within its period, and all the way up at the top, the least shielding in its period, is going to have a very high electronegativity. We also know nitrogen and oxygen, and we'll see all three of these important in particular when we talk about interactions between molecules. Now you might note, noble gases don't appear in this chart. Why not? Under normal circumstances with their full valence shell, we don't often see bonding with noble gases. Now, as noble gases have more weakly held valence electrons, so more shielding, we do occasionally get cases where a noble gas will bond with a very electronegative element like fluorine, but they're left off of the electronegativity scale because under normal circumstances we typically do not see them bond. So we've looked at the effect of nuclear charge, shielding, and electron-electron repulsion in developing periodic trends. Keep in mind, these are just three examples of periodic trends, but the same patterns apply to all of them.